Hello again. The next problem is going to be a 3-mile island problem, meaning steam escaping across a leaking relief valve of some sort or a crack. So I'm going to explain why it's isenthalpic steam expansion, and then we're going to go to solving the problem. So it should be pretty good. So the first thing we do with any problem, right? We go through and look at numbers, make sure they're right. Like this one's 35 psi-A, so that's good. They can trick you with a psi-G, and I don't like that. They can also do a 1500 psi-A, and for some reason there's another 500 psi-A, but they're all A's, so that's important. I don't see any other numbers, so we'll move on. All right. Pressurizer safety valve is leaking by, allowing the dry saturated steam, that's important information, in the pressurizer to flow to the pressurizer relief tank. Alright, so that's probably a quench tank if you're at Arkansas Nuclear 1, or a reactor drain tank if you're at Palo Verde Nuclear Generating Station. So high pressure steam is leaking past the relief valve to a lower pressure tank. The reactor has been shut down and a plant cool down and depressurization are in progress. That's good information. PRT, tank pressure is being maintained at constant 35 psi-A. Alright, so they want to know enthalpy. Enthalpy question, alright? So before I even look at any of the answers, I know that we start right here. Pressure at saturation equals 1500 psi-A. And we're going to need to find the enthalpy, which is going to be H of G at 1500 psi-A and H of G at 500 psi-A. We're going to compare those to see which is higher, and then I'm going to show you that higher enthalpy will equal higher temperature. Alright, so on a nozzle problem, that's what this is. Flow escaping from this, we start with the general energy equation from your generic fundamentals equation conversion sheet. There's going to be the general energy equation, and it's going to be this: G Z2 minus Z1 over G sub C plus V2 squared minus V1 squared over 2G sub C plus specific volume times P2 minus P1 plus U2 minus U1, and then plus Q minus W. So you're given that equation. That's a general energy equation, and you will recall that this term means kinetic energy. Well, kinetic energy is going to go to 0 because, oh, I'm sorry, that's potential energy. Potential energy is right here, mg over z. Mgz is the usual formula for that. There's no big elevation change, so z1 minus z2 is pretty much going to be 0. And let's change that ink to sort of pop out. That's pretty much going to be 0. V2 and V1 are going to be the same thing, so we're going to make this go to 0 either. And this is, of course, kinetic energy. So the velocities aren't that much different for this to change, so we're going to assume that that's 0. And there's no heat being added to or taken from the system because assume there is no ambient heat loss from the tailpipe. So heat, that's 0. And it's not turning a turbine or anything, so there's no work being done in the system. So what we're left with is P2 specific volume minus P1 specific volume plus internal energy and then minus internal energy is going to equal 0. And I forgot to write here that equals 0 too. Oh, equals, excuse me, that equals 0. This entire equation is going to equal 0 because everything's going to balance. All right. So what we're going to get down to is P1 V1 plus P2 V, no, I'm sorry, plus U2 equal U1. Good heavens. P1 V1 plus U1. What's that equal? Well, that's going to be enthalpy at stage 1. It's going to equal P2 V2 plus U2. All right. PV plus U, that's going to be enthalpy. Enthalpy is defined as the pressure volume energy plus internal energy. All right. So enthalpy in equals enthalpy out. So we know that this is an isenthalpic process. Okay, so we're going to describe what happened now with a graph. You may recognize this graph. This is an enthalpy entropy graph. This is the saturation line. Actually, let me get rid of that. This is the saturation line. So our enthalpy is going to be somewhere here on the saturation line. And we're going to throttle it out, and it's going to be isenthalpic, so it's going to go somewhere this way. This is going to be superheat. All right, and this is going to be wet vapor. So something's going to happen. We don't know. It could land anywhere in here, but we're going to figure that out. All right, so first we're going to figure out the enthalpy at 1,500 pounds. Enthalpy at 1,500 pounds is going to be enthalpy G, 1,500. So if you look on page 20 of your steam tables, it's going to be the superheated steam. I'm going to recommend that you use that. You'll be able to find 1,500 very easily. It's the third from the bottom. So 1,500 pounds. It has a saturation temperature of 596.27 and a saturated steam enthalpy of 1169.0 BTUs per pound mass. All right, so that is going to be the enthalpy at the tailpiece. 1,500 is what I'm going to call out. Now, is that saturated? Is that superheated? Well, I really don't know. So, what we need to do, sorry, that's not 1,500. That's going to be 1,500 to 35. Because remember, the tank is at 35 psia. All right. So the way we check if it's superheated or saturated is we look up the H of F at 35 psia and the Hg, the saturated steam enthalpy, at 35 psia, and we see if it falls under there. All right. So at 35 pounds, you're going to look over here on page 15 in the superheated steam table, and it's not going to be there. It's going to go from 30 pounds to 40 pounds. All right, that's okay. So let's go to table 2, and we're going to look up absolute pressure. Again, okay, if you look at page 11, we only have 30 pounds per square inch and 40 pounds per square inch. Well, so that kind of stinks. We may have to interpolate, excuse me. But before we do that, let's go to page 7, which is the saturated steam table, table number 1, using saturated temperatures. And right down here at 260 degrees saturated temperature, we have a corresponding saturation pressure of 35.445. That's close enough. And from that table, I can tell you that the fluid enthalpy of saturated fluid is 228.79 BTUs per pound mass, and the saturated vapor enthalpy is 1167.4 BTUs per pound mass. So if you're looking at these, don't get confused and write down enthalpy FG. That's just the difference between these two. Alright, so we'll call that H sub FG. And that's going to equal to Hg minus Hf. It's just an easy calculator, but it also messes you up quite often. So be sure you get the real enthalpy, and that's the one we want to compare it to, right there. So we're at 1169, and saturation was at 1167.4. So we are superheated steam, but just barely. Okay? In other words, we have gone past 260 degrees, so we're temperature greater than 260 degrees, slightly. Okay? And now we want to compare that, and that is the saturation at 30 psia. Now compare that to enthalpy at 500 psia. And that's, of course, going to be dry saturated steam, so we use H sub G at 500 psia. And now I'm going to go back to page 20 and look at the table 3, superheated steam, because it's superheated and saturated. That's going to help me out. And look on page 19. You'll see that absolute pressure of 500 pounds per square inch has a corresponding saturation temperature of 467.05 degrees and a saturated steam enthalpy of 1205.0. And that's BTUs per pound mass. Okay? And what do I want to say about that? Look at that. That's much, much more. So compare those two. Alright, so this is also going to equal enthalpy of the tailpiece at 500 to 35. Now if you remember, does that fit between H sub F at 35 psia of 228.79 BTUs per pound mass and an H of G, 35 pounds, of 1167.4 BTUs per pound mass? And it most certainly does not, so it's definitely superheated, and it's about 35 degrees superheated. That doesn't correspond to what temperature it is, but that will tell you that it is higher. All right, so we're going to be more superheated because we have more enthalpy. And you can prove that to yourself by going up here on page 15, and you look at 40 pounds absolute pressure, saturation pressure. You'll see you got 1169 is your saturated steam enthalpy, 1169.8. Well, if you superheat from 267 to 280, you get 1176. If you go to 320, you get 1197. So enthalpy is rising as temperature superheat is rising. Right around there. And you can look at 30 if you want, right? So at 30 pounds absolute, your enthalpy sub G, which is going to be saturated steam in the second column, is 1164.1. And if you go 100 to 280 degrees, you're going to have 1197.3. And then up to 320 degrees, you're going to have 1199.1. All right. So given this, if you actually had the time and inclination, you could extrapolate exactly what temperature is, and we'll do that in further problems. All right. But what we need to know now is more superheat means more hot at pressure in the pressurizer of 500 pounds. Okay. So we lowered pressure in the pressurizer and the tailpiece temperature got hotter. We went barely to superheat here, and then we went all the way to superheat over here. Now if you recall from the molar diagram, the superheat curves look something like this. Okay, so we actually scratch that. They were something like this. So let's see, how do I make that? Regardless, heat went up, you'll be able to see it on your molar diagram if you choose to use one. I never use them because they're hard to master when you're under pressure. Alright, so which one of the following describes how the safety valve tailpipe temperature will be affected as pressurizer pressure slowly decreases from 1,500 pounds to 500 pounds? And I'm going to say it does not decrease, it actually increases. So we know that's good. And then because of the entropy of the pressurizer steam will be increasing. Well, that's true. Entropy is going from entropy 1 to some state entropy 2 out here. But does that make temperature go up? Not necessarily. Right? So look at the second one. Because enthalpy of the pressurizer steam will be increasing. It will. And we proved to ourselves that it will make temperature go up. So this correct answer is going to be B. Or you can do what every other GFES student in the known universe has done and say, ooh, it's a 3 Mile Island problem. Enthalpy is the same from the steam to the tailpiece. And that may give you enough to guess off of, if you're so inclined. So that is about all I have to tell you, people. Thank you for your attention.